Hi, everybody. Okay, let's continue now and talk about paramagnetic materials. So in paramagnets, the material contains a high density of microscopic magnetic moments. And the question is, how do these moments behave when they're placed into a magnetic field? And we can kind of imagine how this is going to work. If there's zero field, and if we're at a finite temperature, then we expect that the moments will be randomly oriented by thermal fluctuations, and that the net magnetization will be zero, okay? But if we add a magnetic field, we can imagine that the moments will tend to align in the magnetic field. There we are, tend to align in the magnetic field. And so we'll get some magnetization. But there's always going to be a trade-off between the alignment due to the magnetic field and the thermal fluctuations, which tend to destroy magnetic order. And we'll see how those trade off against each other when we look at this problem in detail. It's kind of a neat problem. It's important enough that you also see it in our statistical mechanics course, but let's go ahead and take a look at it now. There we are. So here's our material that contains N over V magnetic moments per unit volume. Okay. If we're at finite temperature and there's no magnetic field, then they'll be randomly oriented. But if we add a magnetic field, then we expect that they'll tend to order. Okay. And the result will be a trade-off between the thermal effect and the effect of the magnetic field. Okay. Let's assume that the magnetic moment of each dipole is given by minus G mu b times J, where J is the total angular momentum for that moment. And to keep things simple, let's assume that the J is due to one unpaired electron spin. So we'll assume that J is equal to 1/2 and that G is equal to 2, okay? In that case, we can say that each moment has two energy states in a magnetic field, spin up and spin down. The potential energy is lower for the spin up state, okay? But those are the only two states. So the potential energy for the magnetic energy is minus m dot b. And so we found this was plus or minus mu b times b, okay? We're here, the magnetic field we're talking about is the external magnetic field, which we can just take to be mu naught times h. All right. In other words, while our magnetic moment has no magnetic energy in the absence of a magnetic field, when we add a magnetic field, we get two energy states. We get the spin up state and the spin down state. And these are at different energies. And the energy difference between them is just going to be 2 mu b times b. All right. Now, let's see, if we're at finite temperature and our system have these two possible states, what's the relative probability that we'll find the system in one state versus the other? Okay? And what we find in statistical mechanics is that the relative probability is given by a Boltzmann factor. So the relative probability of being in the, let's say, spin down state versus the spin up state is given by e to the minus energy of the spin down state, over kT divided by e to the minus energy of the spin up state divided by kT. Okay? And in this case, we can see that this relative probability would just work out to be e to the minus 2 mu sub b divided by kT. Okay? Very good. All right. And now we can just get an idea for what this formula is telling me. Imagine I have a system and I look at the relative probability of occupancy as a function of this energy, mu b times b. Well, if mu b times b is very small, if it's 0, for example, then the relative probability of occupancy will be e to the 0, or 1. But as I make mu b bigger, let's say I turn up the magnetic field, then, the factor in the exponent will get larger and larger. And so e to the minus that exponent will get smaller and smaller. Like so. Okay? So at high temperature, both states will be occupied at equal probability. If the energy difference is very small, then both states will be occupied with equal probability. But if the energy difference is very large, then only the lower state will be predominantly occupied. We could also imagine what happens if we change the temperature. If we're at a very low temperature, then only the lower energy state will be appreciably occupied. But as we raise the temperature, the term in the exponent here will get smaller and smaller until finally it's so small that we can treat the probability as going like e to the 0. And then both states should be occupied with roughly equal occupancy. Something like that. At the highest temperature, we would get random occupation. I'm trying to draw here, not so well. Whereas at low temperature, only the lower state will be appreciably occupied. Okay? We could say that here, the system is frozen out. Whereas at high temperature, the occupancy is just random. Okay? Now, let's try and describe how the magnetization of such a system would depend on temperature. Okay? So to begin with, let's assume that the total number of magnetic moments is n, and that n, of course, will be just the sum of the number which are spin up and the number which are spin down. And we'll suppose that this is a large number. Okay? If this is a large number, then the ratio and number spin down over number spin up will just be given by this Boltzmann factor, e to the minus 2 mu b over kt. Okay? Because the number will be so large that just the probabilities will describe the result. And in that case, the magnetization will be something that we can calculate. Of course, the magnetization should just be mu b times the number that are spin up minus the number that are spin down. Okay? If we had equal numbers of spin up and spin down, then of course they cancel out and we'd have no net magnetization. It's only when we have an imbalance that we get a finite magnetization. Okay? Okay. It's helpful to rewrite this. We'll write it as mu b times, excuse me, time, we're going to factor out n. So now we're going to have UBN times n up minus n down minus n up plus n down, since of course that's the same thing as the total number. Okay? And now we can work with that. So then the next step, we can replace these with the Boltzmann factor. Here, 1 second. So dividing top and bottom by n up, we get mu b n times 1 minus n down over n up divided by 1 plus n down over n up. Okay? And now this ratio, n down over n up, that's just given by the Boltzmann factor. Very good. Well, this is our result, but it's kind of hard to look at the moment. We can rewrite this and make it a little more compact and easy to understand. Here's what we're going to do. We're going to write the term in parentheses. Well, we're going to factor out a factor of e to the minus mu b over kt from the numerator and from the denominator. So of course that's just multiplying by 1. But then what's left will be e to the plus mu b over kt minus e to the minus mu b over kt. And the denominator will have e to the mu b over kt plus e to the minus mu b over kt. This is a little ugly looking. Let's get a shorthand that we can use just while we're deriving all of this. Let's let x equal mu b times b over kt. And then we can write this a little bit more neatly. The magnetization will be mu b times n times e to the x minus e to the minus x over e to the x plus e to the minus x. Okay, there we go. All right. Now, this last expression can be simplified. At least we can rewrite it. You'll notice that the thing in the numerator looks like hyperbolic sine. And the thing in the denominator looks like hyperbolic cosine. And the ratio of those is a hyperbolic tangent. So we can say that m is equal to mu b times n times the hyperbolic tangent of x, where x is equal to mu b over kt. Okay, and there's our result. So, very good. So now we've found how the magnetization depends on magnetic field and also on temperature. And let's spend a few minutes now and explore this result.